Okay, the last lecture was a little bit of a summit hike. So today we're going to try to relax a little and dig in some of the vistas that we've obtained from the work we did. So we've gone through some mapping. We did a lot of introduction to doing field theory and RG calculations. And so today I'm just going to go through a series of applications. If I don't get all the way through, well, we'll push some of those into the next time. And so we'll just take those as we come. There isn't really, isn't really an outline for this talk because I'm just going to sort of sample some of the things we can do with this formalism. Trying to decide what order. Okay, so let's first talk about something that we've heard a lot from Donnie about, namely the coalescence or coagulation reaction, where A plus A meet and not annihilate, but rather leave one A behind. What's interesting is if you go through the Doi formalism and you map it to a field theory, what you get looks just like what we had before, except that that 2 turns into a 1. Okay? That's it. That's the difference. Which means all the structure of the calculation is identical. There's going to be a few coefficients here and there that get modified. This was pointed out by Politi. So that's already interesting. You sort of know already that it's got to be in the same universality class as horse cube and minus d over 2. You can exploit this to obtain whatever epsilon expansion you did before. You can immediately write down the new one. Is that a question now?
Yeah, there's still a relation between, it's still lambda naught, that the ratio of 1 now, between the quartic and quadratic terms.
That's what changes. The ratio is what changes, and that's why lambda naught itself, of course,
but the ratio is preserved or not?
The ratio is preserved.
It's still preserved.
The ratio is preserved because the kinds of diagrams that renormalize are those bubble diagrams that are the same. So I renormalize this and this the same way, namely by adding this.
Right.
They renormalize identically. The ratio then actually affects universal properties. But the value itself is irrelevant. One kind of interesting way to shortcut having to go back and redo the epsilon expansion even when it's just a matter of putting in some vectors of 2 is to think about a rescaling symmetry. If I rescale phi by a factor of b, if I tilde by the inverse, well, all these bilinear terms, well, this bi, oh my god, is unchanged. This is unchanged. Okay, my initial density changes, but nothing dependent on that asymptotically. And so I can actually use that rescaling to map one right into the other. And so you can immediately conclude that this is at least asymptotically when, say, the initial density is no longer an issue. I can conclude that the coalescence reaction has twice the amplitude as the annihilation, something Danny already was talking about in the empty interval context, so we can get it in the field theory context. An interesting variant on this is what if you allow both processes with some relative chance. So there's a when they meet and react, there's a probability p that it's a coalescence, probably 1 minus p that it's an annihilation. Well, you put in the Dwight Hamiltonian, you map it here, you work out that coefficient, and you get this relation, and that's exercise 1 over there on the board. So it's really a very straightforward approach.
So what happened to P?
Sorry?
What happened to P?
P.
So you're not writing that for the equation.
No, well, this corresponds to p equals 1. And so you're supposed to generalize it.
So for the excess of 1, T should be 1 plus T.
No. No. You have to, probably have to write a little bit. But it's pretty simple, but it's not that. Okay. Let's talk about something we thought we were done with, but we should be thinking clearly about this. What about when d is greater than 2? Remember that when we compared these two vertices, we said, oh, this one had a short time problem, but that's not a real problem because it's the lattice cutoff, something regulates that. And in long times, it was negligible. Okay? The way you can think of this, and it's quite accurate to think of it that way, if you think about this being a 3-point vertex getting renormalized by adding 4-point vertices, the effect of the 4-point vertex is negligible. asymptotically. You can say that for d greater than 2, this thing flows to 0. Now you might say, fine, we saw that with the beta function, right? When we wrote down the beta function describing the coupling with the renormalization clause, we have beta of gr. For d greater than 2, it came in with a finite slope. And so basically under renormalization, it goes to 0. All sounds very simple, but then you ask, well, wait a minute, why does the 3-point vertex flow to 0 too? Right? You said they renormalize identically. Okay. When d is greater than 2, you got to sometimes be careful. There are things that are called dangerous irrelevant variables. And that's one of them. I can't really make that flow to 0, even though this one does flow to 0. And one reason to see why is exactly that rescaling symmetry. Okay. I can choose to rescale phi and phi tilde by b and minus b and change this term and this term alone in the field theory. Okay. So what I really want to do when I'm imagining those flows is to imagine that I essentially keep this fixed by some rescaling symmetry while I'm letting the flow go on. And then the 4-point vertex basically goes to 0. This I can't get rid of. If I get rid of it, I've lost the reaction. I've lost my physical system. So, the important conclusion from this, first of all, is when you're sending things to 0 because they're irrelevant, you should always be careful. Right? Sometimes they can rear their heads and demand that you keep them. But the other really significant thing to take from this is once I've understood that this is linear, I can do that delta function trick and pop down a reaction diffusion equation without noise. Right? No Langevin formalism here. This is a reaction diffusion equation. So what the field theory gives us with RG analysis is a criterion for when reaction diffusion equations are valid. That's a great thing to know because then when you're studying this problem at d equals 3, you can just plug that down and start solving. Okay?
Sir,
yes?
I did not understand the argument because the beta function is the says how evolves the 4-point function, the dimensionless 4-point function.
Right.
Okay, and that goes to 0. But the dimensionful 4-point function doesn't go to 0. It goes to a non-universal value that can be calculated for a given. Okay.
It goes to, well, its impact is to effectively renormalize the 3-point vertex. The total impact of the 4-point function is, 1, to give you some transients. You can create some diagrams that are subleading in time by having it. But 2, when you create these bubble diagrams, it gives you a finite renormalization of, a finite non-universal renormalization of the 3-point function as it's flowing to, well, right. So again, when you're doing sort of the RG flow equations, you're always comparing 2 different points, right? Over here at T naught and at late T. And I agree that, well, I'd rather not get too hung up on this at this point.
Well, we can discuss
right.
that after. But moreover, one other point, there are many other couplings that are generated along the flow.
Yeah. But they're irrelevant. I mean, there's a power coupling argument.
Okay, then that means that for universal properties, you may be fixed
right.
to this equation. But
Absolutely.
For non-universal quantities, you will need to take into account all those.
Absolutely. This would only be a valid. You can only validly go to the reaction diffusion equation if you're interested in long-time properties and essentially universal quantities.
Yeah.
You can construct interesting, well, at least you can construct quantities that would not be described by that equation. Yep.
If you didn't know about that scaling symmetry, how would you later find out about dangerous irrelevant variables?
Well, that's always that's one of the little pitfalls. You know, we teach RG as a sort of cookie cutter method, but there's these little holes you can fall in, and that's one of them. Usually something falls apart in a what's that? Big holes. That's a big hole. But usually something falls apart in a big noticeable way. Like here, I send them all to 0. And say, wait a minute, I don't have any more reactions, and now you're saying the density's constant. That's got to be wrong. and then go back and think about what I do wrong.
But you can even see even the quartic term is, in a sense, it's a dangerously irrelevant variable because you get an equation that has no noise. And so if you compute any quantity that depends on noise, what kind of fluctuations apply, you'll get zero. And so it sets to depend.
For certain quantities, it would be dangerous and irrelevant variable. For calculating the density, it's not.
But it's a question of what you calculate. So certain quantities, if they sensitively depend on variables you set, irrelevant variables you set to zero, that variable is dangerously irrelevant.
Perfect.
So now if I look at this, I'm really confused. You have lambda 0, phi tilde squared, phi squared as your quartic term.
This one?
Yeah, the one you sent to 0.
Yeah.
And then you have lambda 0, phi tilde, phi squared. So
Yeah.
what is the engineering dimension of lambda 0?
Well, if I rescale the fields by a dimensionful, this maybe would make it more clear. When I talk about
there is no field denomination, right? In this problem, it's only vertex denomination. So you did not rescale the field.
No, but the rescaling symmetry is always there for me to do if I want. And I could choose to rescale by lambda naught to make this dimensionless. And that's a useful reference point to analyze the flows for d greater than 2. This is probably how I should have started. Right? So if I scale phi, dividing it by lambda naught, and if I tilde multiplying by lambda naught, this is unchanged. This goes to a dimensionless prefactor. I analyze the flows from that perspective. Okay. And I'm free to do that. It's a symmetry of the model. So it's the proper vantage point to try to understand the flow.
So the dimension after all of this rescaling of the cubic term is, you're saying, 0. The engineering dimension is 0.
Yes, once you do that rescaling.
Sorry, not engineering.
The power counting dimension, whatever. Yeah.
See, so it's quartic, so just to make sure I get this right, so the upper critical dimension is 4?
No, the upper critical dimension turns out to be 2 for this because, well, basically, if you don't do the rescaling and then you just look at, do the power counting, it turns out to be 2. We can talk about it. And it has to do with random walk properties.
So it's mean field in 3 dimensions.
Yes. And we're sort of saying we understand that. Let me put this up over here as I'm going to the line. It'll say out, but there's a few lessons to take from this. So for d greater than 2, we can get asymptotic, let's say. And yes, we can measure certain quantities where this wouldn't be true, but an asymptotic effective action is equal to reaction to. Okay? So that's one of the things we learned from this, and we're going to use that when we want to. Let me just quickly put up, since the lights are on anyway, the other things we should take from this. I'm not going to go back through another long, detailed RG calculation. I'm sure you'll be happy to hear that. But let's remember what we kind of got out of that. When we analyzed the flows, our initial densities didn't go to any kind of fixed point. They were just blowing up, 2 to the d over 2. Our couplings went to some order epsilon fixed point, where epsilon is 2 minus d, or they went as 1 over log t, d equals 2. And the other thing is that we got an overall t to the minus d over 2 factor. That's basically because when we're doing the RG flow, so sort of the rescaling, density as we mentioned, we get that back direction. If I'm doing a correlation function, then it might be that squared or something like that. Okay? So those are going to be things we're going to invoke as convenient.
I think a question. So when you do the normalization
Is the 4-point vertex?
Yes. And actually, you need to integrate diagrams of the moment space from 0 to infinity. So actually, for the system, you should have a cutoff for the moment.
Sure.
If you do that case, there will be some corrections.
There will be some what?
Corrections. And for the cross terms will not be calculated.
Oh, well, man, I'm not quite sure I get, but I will say that this is certainly not lambda naught. The influence of those integrals out to the cutoff are going to change this value. I'm not sure that's what you meant.
In this case, you say the whole particle flux goes to zero.
Well, what I mean is that I can instead do an effective field theory that doesn't have the 4-point vortex, but has new rescaled couplings, and I can get the same answers. That's what I mean. Okay.
Another way of saying all this discussion, there's always noise. I mean, noise does not go away. That's absolutely true. So this is what Nicholas was saying, what you were saying, what Leo was saying. Right? It just doesn't really matter for certain properties.
You would probably
that's true for any mean field system. If you talk about the 5 to the 4 model, there's always the statement mean field is exact about 4 dimensions. That's nonsense also. It's only exact for the critical exponents. There's still nonlinearities, there's still fluctuations, they just don't qualitatively change your exponents. They're still shifting TC around, they're still affecting non-universal properties, and there's always noise.
No,
it's the same story here.
I would say even some universal properties. You can come up with a physical observable that sensitively depends on quantity you set to zero.
Well, that's semantics now. I would not call it a universal quantity. Sure. Yes, there's always something that's affected by fluctuations or not.
Okay. I think we'll save the rest of this for this discussion that's going to happen.
Thank you.
Okay, but thanks for that. Let's go on to a slightly different reaction. What if we need to have 3 particles meet? This is a higher order reaction. It requires more particles. First thing you ought to do always is write down the rate equation. So here we are, and it's not too much work to show that the predicts decay as 1 over the square root of time rather than 1 over t. If you compare that to t to the minus d over 2, right, that's what we get when we do the simple dimensional analysis. We see that they match not in 2 dimensions, but in 1 dimension. Our upper critical dimension actually gets shifted down to 1. Which is basically has to do with the statistics of 3 random walkers meeting. When does that become a probability 1 event? And that happens in 1 dimension. If you map this through, so L here means 0, 1, or 2. I'm still considering only decays, things that remove particles from the system. If you map that to the Dwight Hamiltonian, it's probably not too surprising that you'll end up with vertices that look like this, these little spidery guys. They all require 3 incoming lines because that's what you need to get a reaction going. You do get all 3 of these vertices for any one of those L's due to the field shift, but the relative weights of them depend on which reactions you have. So in that sense, everything goes pretty much identical. Now let me, so first of all, this is mostly interesting at its critical dimension, right? I don't know how to do a 0.67 dimensional simulation. But on the other hand, it's kind of nice that, remember, at the critical dimension is when we predicted the density amplitude exactly, not as a perturbative expansion in epsilon, but as an exact one. So now we can do the same in 1 dimension, which is where simulations are the most powerful, and so we got a good place to test ourselves. Well, all I'm going to do is appeal to the result from last time to say that, okay, if I first sum up the tree diagrams, I can put in my n-naught flow, let n-naught get large, and it again drops out. Right? This is square root, so the n-naught gets large, it cancels. So I'm taking care of this. I'm going to ultimately replace this with a dimensionless g-naught, which I developed in an expansion in gr, and that's flowing to 0. Whoops, I'm getting ahead of myself. Here's the expansion in gr. Okay, this would be the tree diagrams. The 1 loop corrections will be in order square root of gr higher. The 2 loop will be an order square root of gr higher still. This is a very weird expansion, right? It's each term in that expansion is an infinite sum, so I can get things that are not analytic in gr. But I can also show, without too much work, that the 2 loop order diagrams are all square root gr and higher. Right? So it's a controlled expansion, albeit not an analytic one. It wasn't analytic last time either, though, right? We started with -1 and then 0. This is that overall factor that we get. And so then we just plug in the logarithm here. This goes like 1 over log. When you think I just go for some other time. Put in the 1 over log, and out you get a universal amplitude. But a kind of interesting thing happens that helps us in comparison to the simulations, which is that the leading correction is also universal. The flow, let me back up a second. In this flow to 0, this tau here is where I hit a lot of ignorant. That tau depends on whatever short distance cutoff I have and exactly the nature of the cutoff, whether it's a capture radius or a lattice spacing or whatever. It's very non-universal. These coefficients are universal because they just are some calculation from the loop diagram. So what the RG assures me is that once I get it in terms of an expansion, in terms of GR, all the singularities are gone. So these are nice, well-behaved numbers. Okay? But here's the non-universality of RG. There's also non-universality in the sub-leading time term. Well, because I've got this square root here, right, that's log t minus log tau, and when I expand that out, it pops way down here. It doesn't happen in d equals 2 for the A plus A reaction, because there I don't have square root. In that case, my leading correction is already non-universal. But here it pops down one more order, which is very handy because we can do some simulations. This was done by an undergraduate student with me. And what we're plotting here is the density scaled by the expected time dependence. So it should be going to a horizontal line. Okay? And in fact, if you calculate this A, it's that green line. You can see the green line. And the data don't match super well. But then you realize, okay, what if I include this term as well? That's what the blue line is. Okay, so we are not proving that these numbers are correct. The data are not capable of doing that. Clearly, it's always a problem with logarithms, right? Unless you have some way to estimate this tau, you're really going to have some trouble. But at least it's consistent, I would say, right? If putting in the first order correction did that, it's not too surprising that higher order corrections might bring us down to the red line. Okay. What if we wanted a different kind of test? I really like this one. We can leave the realm of diffusion for a minute. We can allow hops of size L governed by some probability distribution with the power law tail. This tail is indexed by parameter sigma. When sigma is greater than 2, even though you have this power law tail, your long time motion is still diffusive. But when sigma is less than 2, that means the tail reaches farther. These relatively rare, really large jumps dominate the long-term transport. That's called the Levy flight. You can measure, for example, the root mean square displacement from some starting point. That goes like square root of t for diffusion. But if sigma is less than 2, and only for sigma less than 2, it grows faster than square root of t, 1 over 6. That's sometimes called super diffusive behavior. If you map this through to the field theory and squint a little bit, the propagator changes from having a k squared to a k to the sigma. Okay. It does a few more things, but this is when you put that in, you've got the dominant piece. That changes things. Remember, we identified that critical dimension of 2 by comparing the loop diagram, the one loop correction, to the vertex. Well, you can imagine that the time dependence of that loop diagram is going to change here. And you can pretty much scale it right out, right? Because here, t and k were related by power 2, and here they're related by power sigma. And so, I'm not going to go through it, but it's a pretty straightforward exercise to show that DC changes from to the sigma. Okay? And that means we can do an epsilon expansion. The numbers will be different because, the loop evaluates to a different number than it did when D was 2. And what's really cute about this is I can now try, or Dan Vernon can now try to make epsilon small, right? When we were doing an epsilon expansion about d equals 2, and we wanted to compare it to exact solutions or simulations at d equals 1, epsilon is 1. But here, he's plotting on this axis 1 plus epsilon, but basically this is epsilon 0 out to epsilon 1, and the amplitude. So data is the dots, and the line is his RG calculation, and you can see that once you get epsilon small, it works pretty well. Okay? So we can't easily change dimension, but in some cases we can change the upper critical dimension. And this is one of those. Any questions so far? Yes, Joe.
Did you try subdiffusing random walks?
People have studied that. I was trying to remember last night what came out of that. I don't think it turns out to be that interesting. You can put in a waiting time that's somehow power law distributed, so you get stopped for a while and you get stopped for a while. But
would you check the critical dimension up, like to 3 or 4?
no, it doesn't do that, which is why I think it isn't especially interesting. It was a long time ago when I saw that paper. I don't remember what they came out with. Yeah, Neil?
I was going to say, so you literally take if I think of the field theory, just the quadratic term is I omega minus dk to the sigma.
Yeah.
That's,
I mean, you sort of have the dk squared term is still there too, but it's kind of irrelevant at the scale where you're
but the interaction terms, are the terms the same or no?
Yeah, the reaction is identical. You don't change anything there. Okay. Right. It only changes the propagator. Yeah.
But I guess the propagator wasn't renormalizing anyway.
That's right.
It doesn't really help you that much. If you had.
It doesn't really change anything except that it makes your expansion better. That's all. Okay, because now we're going to go into a slightly different topic. This would be the first point at which a chemist would show any interest in what we're talking about. We should have at least 2 species when we have a reaction. When I write A plus B goes to 0, I'm not saying that they've somehow pooped out of existence. I'm saying they reacted and formed some product that we're choosing not to care about. One interesting thing to do, and has been done somewhat, is to instead keep track of the product and put in a back reaction and study the approach to equilibrium and things like that. We're not going to go there. The first and most important thing to know about this system to get started is to realize you've got a conservation law. If you think about the number of A particles and the number of B particles going into a reaction, if you knock them both down by 1, you haven't changed the difference. You can't change the difference. Okay? And so this density difference is a constant. That's a statement as written, I guess, about the average, but this really applies locally. Okay? That's a lot of math. Okay, let's step through this. Really not too bad. Rate equations. All right, the probability of the reaction occurring is a product of the densities, and it knocks B down and it knocks A down the same way. Identical rate equations. But I get 2 quite different behaviors out of those 2 rate equations, depending on how I start the system out. Because again, there's conservation law. Generally, when you have conservation laws, how you start things out can matter. So I can start things with an equal amount of A and B. And this says, well, so they're going to be equal for all time, because that constant's 0. And so I can say, just call this A, and now we get the plain old 1 over T that we always got before for A plus A. All right? The rate equation says, if I'm starting with equal initial densities, I get 1 over T. I'm not saying that everything is going to be the same, but that's what the rate equation is. But looking at it, if I start out with an excess of A particles, what's going to happen is, pretty quickly, it's going to eat up almost all the B particles. So if you're an A particle and you want to, annihilate, you got to do it early, because pretty soon you're just going to be running around with a density of A naught minus B naught, with almost no B particles around to react with, and that'll be the rest of your life. We can then put that back into the B equation. So what if you are one of those lucky, rather frightened B particles surviving? What you'll see is that in fact you're going to have your density change exponentially. The rate equations predict power law decay if we have equal initial densities, but approach to a constant and an exponential decay if they're unequal. That's the first thing you should do, rate equation. Usually, that's presumed to be the same thing as if you do the reaction diffusion equation. Putting in some diffusion term here, well, it's just average over space, and then it goes away again, and I'm back to the rate equations. Here, that doesn't work so simply. You've got to be a little more careful. One thing I'd like to observe, though, is the arguments I was making earlier that maybe a few people in the room bought, is that we can at least argue from the RG, I got here. We're going to show that for D greater than 2, that for this system we also get reaction diffusion equations as and how to do that. let's not worry about that yet. I realize I got out of order. Let's just take them as a system of interest, or some math of interest. One thing that you can show, so let's talk about the equal density case. If D is less than 4, you get asymptotic segregation. So Donnie was talking about this some. It says if I look in one region, I'll find around that neighborhood only A particles, or in a different region only B particles. Okay, with fairly well-defined boundaries between them. It doesn't happen above 4 dimensions, but in less than 4 dimensions it does. And it has some interesting properties then. First of all, this first equation just follows from the symmetry. If I'm starting with equal initial densities, right, then the B density and the A density have to be the same. But now if you think about the fact that in each region, if I'm averaging this over space, in each region only this or that is contributing. Okay? So if I took an absolute value here, that thing is going to average to the same quantity as that. That's a statement about segregation.
Can you say that again? What's the statement?
The statement about segregation is if I take the difference field, absolute value, at any point in space, that's either just giving me the B density or the A density. So if I average it over all space, it's just giving me the B average plus the A average.
So this is only true for if you start with equal density.
Only true for equal densities, absolutely. Absolutely. You don't get the segregation otherwise. Because the A particles win. They're everywhere.
But I don't quite understand. When you say A0 equals to B0, that's average or?
No, this is an initial condition.
But in it?
For that special initial
no
condition.
noise?
Well, I mean, I can throw down, I get to control how many particles I'm starting with. No, the fluctuations about those is going to be significant. We're going to get to that.
Okay, so this is assuming.
Poisson initial conditions with equal means.
Equal means, okay.
Is there any relation between A and B? EA and B?
Ah, right. Right now, I'm assuming they're possibly distinct, and this statement would still be true. Ramsey and Leibowitz have rigorous proof of the segregation occurring for D less than 4, even with unequal diffusion.
Is this only correct as 8 times?
Yes. Yeah, that's the squiggle.
The squiggle means asymptotically in the right dimension.
Yeah, in this case, that's the squiggle. That's most of the time what it means. Okay, let's go a little further with this. And this was the seminal work by Vollmayr-Lee that Donnie was talking about earlier. Let's just make life a little simpler and consider the dA equals dB case. We don't have to, by the way, but let's just do it. Then, if you take the difference between those two equations, let me back that up a second. Notice that the reaction term is the same for both, right? It has to be. That's our conservation law, right? If I take away an A, I've got to take away a B. So if I subtract one equation from the other, the reaction term drops out. And I've got plain old linear diffusion. Okay, the difference field evolves by the diffusion equation. And one property of that is that no matter what distribution you start with, if you evolve by the diffusion equation long enough, you're Gaussian. So you can say, all right, maybe let's simplify things. Assume it's starting Gaussian. Well, let's not worry about that. Let's now think about the fluctuations in those Poisson initial conditions. All right? That says if I go in and measure that difference field to naught here means t equals 0. And of course, if I average A minus B at t equals 0, it's 0. I'm talking about the equal initial conditions here. But if I take the difference field at one point and at another point, product and average, this is where you get the n naught delta correlated fluctuations. So, what you can show then, since these only evolve by the diffusion equation, is that at some later time, the squared field average is given by this value. So I'm basically telling you that, but you can almost see it. It's going to be, I've got to diffuse this one to some point t, and I've got to diffuse this one to some point t, average over it. Here's the strength of what survives the average. Here's the loop of those two things along t. And then, if you take into account segregation and remembering that it's a Gaussian field, it's not too much work to get to this amplitude. That's one of your homework problems there. So you get to take that as a given. And Poisson and Vollmayr-Lee wrote that down. It's been tested numerically. It seems to be right in D equals 1, 2, and 3. Okay? Any questions? All right. what about the field theory? What do we learn from that? Well, first of all, propagators, not surprising. You just get the usual ones, which is diffusion still. The vertices involve having an A and a B. I'm using solid lines for A, dashed lines for B. Having an A and a B mean and an A tilde coming out, or an equivalent vertex with a B tilde coming out, or this 4-point. And you don't have to look too hard at it before you realize that the renormalization structure is going to be identical. You can only get those same sets of bubbles. And so everything goes through pretty much as before. And so the critical dimension is 2, and for D less than 2, you go to an order epsilon fixed point and say, wait a minute, what happened to 4? Right? What is this business about 4? You'll find a lot of papers in the literature calling for a critical dimension. She found John Hardy was calling for a critical dimension. And he knows it. It just slips out. We can't help ourselves. 4 is not the upper critical dimension. 2 is. You say, well, wait a minute. Nothing happened to 2. I just said that Toussaint Wilczek result holds in D equals 3, 2, 1. That's right. And that's actually more or less one of the outstanding puzzles in this business is why D equals 2 doesn't have any signature there. But I will say, D equals 2 has plenty of signature elsewhere. So we're pretty sure that part's right. Let's just go back and revisit what's going on in 4. So now I can say that the RG predicts that our asymptotic results are given by an effective field theory that doesn't have the 4-point vertex, and that's equivalent to the reaction diffusion equations. So basically at that point we'd say, yeah, Toussaint and Wilczek not only were studying an approximate theory, the reaction diffusion equations, they were just studying the exact effective theory, and therefore their result we would expect to hold. That theory, the reaction diffusion equations, predicts this change in D equals 4. And it's just a property of whether the fluctuations in the initial conditions propagate through the conservation law to dominate at late times or not. That's all that's going on. It's a switch from one reaction diffusion equation behavior to another reaction diffusion. What happens at D equals 2? Well, I can give you 2 examples where things show up and know what the critical dimension is. One is, what if we had those unequal initial conditions again? We saw that the rate equations predicted exponential decay. The reaction diffusion equations also predict exponential decay. So this is basically the reaction diffusion result. But when you're in D equals 2, there are log corrections to that, and when you're in D less than 2, it decays sub-exponential. And those are exact results from Branson and Leibowitz. Lately, Alan Bray's done some very nice, Bray and White have done some very nice work where they get the coefficients exactly. And we can also get it from the RG if we just remember our little recipe here. We get the light on. Our little recipe says when we have a density, there's one right up there, let's replace it with T to the D over 2. I should put one more thing in there. The actual T in that RG flow, this T was what we set for the normalization point, right? So that went to T naught. This became the T to the D over 2. This goes to an order epsilon fixed point. There we are. Or, this when D equals 2, then T to the D over 2 is just T, and this is dying logarithmically, and there we are. Okay? So, yeah, kludgy and wavy, but we are unsurprised by the results from the perspective of the energy calculation. That's one example of what happens at D equals 2. Here's another interesting one. We can set up these reaction zones. What if you have, this is an A density that extends all the way to infinity in that direction. This is a B density that extends all the way to infinity in that direction. Initially, they are going right up next to each other. Okay, and then that's T equals 0, you let it go. So reactions can only happen where the two meet. After some time, most of the region of A will still be unreacted. It's only going to be regions out to a range of D over a square root of time. This is called a depletion region, and it's the diffusion length, because those are particles that have had a chance to diffuse into the reaction zone. If you're farther away, no chance. Okay? So that is T to the 1/2. But then you have this long linear profile where out here there's still no reactions going on. You have a boundary condition essentially that you've got to have this density here and more or less vanish from here. So that's why you have a slope, which represents a current when you're talking about diffusion. But it's a straight line because that's all you've got. Right? Now in here, then the A and the B mean, and we have reactions occurring. R of x is a rate of reaction as a function of x. Or if we were doing A plus B goes to C, we could talk about a rate of production of C. Where is C being produced? And you can study this at the reaction diffusion equation level, and that was first done by Galfi and Raj. And it's actually surprisingly complicated analysis. I mean, that was probably the most complicated mean field analysis I've ever done. Just following what they did was the hardest I've ever done. And what they got out of it was that this width scales, for example, with an exponent of 2 to the 1/6. You can ask another question: what is the typical interparticle spacing here? Here I know what it is, right? I've got a constant density, so my interparticle spacing, well, it's constant. And here, it's presumably growing with time, with what power? And what comes out of the Galfi-Raj analysis is that it grows as a t to the 1/3e. Okay? Well, from our field theory point of view, we can make the argument that those results should hold for any d greater than 2. But for d less than 2, we would expect that behavior to be modified, and so here are modified exponents. I have a little argument for where those come from, but I think in view of the time I'm going to save it. I'm happy to talk to anyone later about it. There is, of course, the borderline case of d equals 2. And you get these values match there, and you get Loewe corrections. That's the usual thing happens. And I should add that there is a very related problem. This is like having a certain current of particles directed in, and this is another current of particles directed in. So you could actually set up a steady state problem, right? Or instead of having this, you just got fixed currents. And you can analyze that problem, and that's what Ben Naim and Redner did, and you can essentially get out all the scaling behavior in that viewpoint as well. Very simple relation back and forth. Any questions on that? Yes?
Based on that, so the basic analysis, so you're saying if you did the reaction stuff, at the end of the day, your reaction, the coefficient is going to 0. So you don't have this earlier problem of English irrelevance of the reaction coefficient, right? So you can do everything from just assuming there is a Gaussian fluctuation in a region, and that's a state.
Yes, for d greater than 2.
A difference, whatever that states.
Yes.
Okay.
Exactly. Yep. By the way, that A minus, so one clue about, let's go back to that question. So why doesn't d equals 2 or d equals 1 show anything interesting, let's say non-Toussaint-Wilczek, due to the renormalization? So we got that t to the minus d over 4, and then the amplitude doesn't seem to care about the fact that we're getting renormalization. Well, again, if you think about where it came from that A minus B difference field diffusing in. That satisfies the diffusion equation exactly, in spite of all of the fluctuations. It's not hard to show. It's, again, just the conservation law. And so that really seems to be the case. That you get some kind of super universality due to that mode. We can't actually show it, but it does seem to be true.
Let's say, just to support that by simulations, if you add that, you see that the next leading term is the standard thing you would get from a plus a to 0. So it's t to the minus d over 2 in 1 and 2 dimensions with the Loewe corrections. And it's just t to the minus 1. So it's
subleading term shows that.
It's a subleading term where all this change.
Okay, whoops, I'm going too far. Now I'm going to spend the rest of the time talking about something I've been working on more recently that's surprisingly rich. I don't know how much we'll get to, but we'll see. So first of all, let's start with the trapping reaction. This isn't quite the full thing of what I'm considering, but let's understand that first. So this is saying that what if A plus B, when they meet, the A is a trap, the B is a particle, the A is a trap. They're both diffusing, or not, but the A basically has no idea the B ever existed, right? It just goes on its way eating up B's and not noticing them. And the B's have a bad time whenever they meet an A. They could, in principle, have different diffusion constants. We will introduce this dimensionless ratio that's the ratio of a particle to trap diffusion. Okay? If you write down the rate equations, the first thing you can see is that, of course, the A density is not going to change. It can't. So I get plain old exponential decay. By the way, this is exactly the same thing as the asymptotic limit of A plus B goes to 0 with unequal initial conditions. Because after all, once you're down in that regime where almost all the B's have annihilated, there's only a few B's left, it's exactly the same situation. Okay. The one A that B will happily, will be able to pick off is irrelevant. Now, there's a singular limit in here that we're going to stay away from. If you set the traps to be stationary, you get to this non-square Valentine result that Downey was talking about. So it's a stretched exponential of a certain kind. And it's basically because in those stationary traps, which are Poisson distributed, there's a few large voids, right? Rare but large voids. And if a B particle happens to get in there, it gets to stay there, right? Until it's foolish enough to diffuse out, it gets to live. Okay. As soon as I let those things, the A particles move, I still have voids, right? They're still Poisson distributed, but the voids are dynamic. They're moving around. And so a B particle can't park in a void, right? It's got to be easy enough to keep moving where the voids are, which is much less likely to do. So we're not going to be able to connect down to that limit. So let's just consider the case where D is at least finite. Okay, and again, we'd expect this great equation to be correct for D greater than 2, but what happens for D less than 2? Well, like I said, this is basically the A plus B goes to 0 limit, so it's the same result. But now let's go on. Let's put in a variation on the model. What if, while that's going on, that's going to stay the same. Particle meets a trap, it's dead. Traps don't notice the particles. But what if the traps actually are annihilating each other? Okay, and we'll just put in either one of these two reactions that we're very comfortable with. I can write down the rate equation to get out this result. This is all summarized, stuff you already know. Okay? Let's look at what that does. Now I have time going up. Now you have time going down. That's something about our personalities, I don't know. But if you're one of these blue B particles trying to survive in a sea of traps, you're going to be really happy whenever that happens, right? That's going to give you a better chance at survival. So maybe we can do a little better than exponential decay. If you go to the rate equations, and you plug in for A here, we can do the A one separately, right? Because it doesn't care about B at all. We just plug in the solution that we got, and you find that B actually does now decay some power law. So we switch from exponential to power law decay by adding that trap reaction. Now what's very interesting about this exponent, at the rate equation level, the exponent is non-universal. It's not 1 or d over 2 or square root or anything like that. It's a ratio of these non-universal constants. Okay? So that's kind of unique in two, or interesting in two ways. Power law and it's non-universal. When you do the RG calculation for this, it's not an elementary exercise. You restore the universality of the exponent. Okay? It is controlled by a universal RG fixed point for d less than 2. What I'm going to give a little bit of survey now is results that we can get from, there are a few exact solutions available in one dimension, what the RG calculations show. I'm probably not going to say much about Shmolakowski's theory. Yes?
So why isn't this also dominated by rare events where the traps, you take a particle and all the traps around it rarely?
Well, in some sense it is what I mean by saying the fluctuations matter for d less than 2. But they're not static rare events. Static rare events are in a different category than dynamic ones. Because I can't expect my B particle to know exactly how to move around with the void, right? The void isn't even going to stay open. It's going to close and a different one's going to open somewhere else. My B particle can't get there.
Sorry, one question.
Yeah.
You say that the decay exponent is universal for D smaller than 2, but for...
What happens at 2?
Yeah.
It's very pathological. Yeah. In fact, I would say it's not clear. There's disagreement about how to interpret it. You certainly get log corrections. The reason he's asking is usually, your RG corrected exponents match your mean field exponent at the critical upper critical dimension, and then just have some log corrections. And that does not happen here. And what does happen and how that crossover occurs is not crystal clear. Okay, so let's just quick. There's three main exact solutions to know about. If D prime is 0, that's the B particles, right? If the B particles are sitting there. Now picture this. You've got your A particles, the traps, moving around doing A plus A goes to 0 or A plus A goes to A. And any place they've ever swept through, they're going to eat up the B particles, which are just sitting there. So what the B density is really doing is measuring the parts of space that have never seen a walker. All they're doing is measuring what's called a persistence exponent. You imagine how much, which parts of the number line never saw a random walker in that A plus A. And so that's actually where the name theta came from, because that's a conventional exponent used in persistence problems. And for 1D, that's solved by Derrida and I forget exactly who his co-workers were, for all mixtures of A plus A goes to 0 and A plus A goes to A. And basically we're taking advantage of this mapping to the Q-state class model that Donnie was talking about, and solving it in that context for any Q, which maps back to any P. A different thing happens when you have A plus A goes to A, you get a three-walker problem. So here's I'll draw the A's in white. Okay, this from A plus A goes to A. This walker is trying to survive. It pays no attention to the fact that these two coalesce, right? All it knows is it's got a left neighbor and a right neighbor that are doing random walks. And for that problem, that fully describes the survival probability. I don't need to know about any of the other particles. It only happens when there's no annihilation, pure coalescence. And so that was solved by Fisher and Delphine for all ratios of diffusion constants. And then there's a special case where the thing's so symmetric that the B is just like an A. Equal diffusion constants, and the A's are annihilating. So basically what happens to an A when it meets an A? It gets killed. What happens to the B when it meets an A? It gets killed. So they're dead. And then we get the C to 0. I'm going to skip Schmalkowski's theory, unfortunately. So if you do the RG calculation, which was done in different ways by different people, and it came out with the same result. That's always nice when that happens. The leading order, you get this thing. This is the ratio of the diffusion constants. This is the mixture of the trap reactions. This is an explicit function, but it is not illuminating. I'm not going to write it down. I'm going to show you graphically. And the point is the calculation demonstrates the universality. I had a student, Bob Rose, who did a lot of simulations. We came up with a kind of cool Monte Carlo technique that did a lot of, the statistics converge faster with this technique. And what you can see is this is just the density on a log-log plot for a variety of cases. And yeah, we can get power laws pretty easily. We can measure exponents. Just a little survey here. These are going to be the case where they have equal diffusion constants. Okay, the trap and the particle diffusing. This axis is what kind of trap reaction. Here it's all annihilation. Here it's all coalescence. The blues things are data from our simulations. The red curve, the sort of magenta squares are the exact solutions. This matches the Derrida. This is the Delphine, Fisher-Delphine. You can see the RG actually, surprisingly, the one loop RG is decent and surprisingly hits the exact solution. I think that's a coincidence. You go over here, you go to the pure annihilation. That's where we got that Fisher solution, right? Or we got a whole magenta curve. You see our technique work. I didn't even bother putting error bars on there. And the RG is doing great. And then, well, it doesn't always do great. Did okay for the exact solutions, but the point is it's a truncated expansion, and truncated expansions sometimes fall down. And yeah, this one just fell down. Schmalkowski is redeeming itself here. Okay, what am I plotting? So this is changing the relative diffusion rate. So basically, if you're trying to study the case where that B particle is really running around fast, which is kind of suicidal, right? If you're a B particle in that situation, your best strategy is to be as stationary as possible. Schmalkowski understands that in the RG, the truncated rate. All right, let's go a step further because this was all it's kind of a standard undergraduate project. I kind of knew what he was going to get, and just the interesting thing would be to see how good quality of the data were. And so then we were looking at correlation functions, and what's interesting is that if you look at the trap correlation functions, it's a universal function. It was calculated by Massa and Abraham, And it's the same function regardless of whether you have annihilation or coalescence or any combination of the two. And the data are very consistent with that. And then you look at the trap particle correlations. So they're anti-correlated, right? Your particle is most likely to survive if it's not near a trap. And a variety of conditions here. Certainly, now it depends on those parameters. If I change the fusion constant, here's some more. Okay, so everything's... But the point is I'm doing scaling classes here, right? And the way I do the scaling class, I should point that out. You take the connected correlation function, so you basically subtract off the density squared. So that means at large distances it's going to go to 0. But of course everything's decaying, so to kind of scale that out, you divide by the densities. So everything's scaling class just nice. And oops. When we try to study the particle correlation functions exactly the same way, these are just two different cases. Every case does this though. Different times, so all the blue curves are the same system but different times. And the green curves are the same system but different times. I'm scaling the x-axis by the diffusion length. The y-axis is not scaling at all. The problem here is I've got an anomalous dimension that's cropped up. So if I just study the self-correlation at the same point, that goes to a constant when I divide by the density squared. That goes to a constant in those two cases, but here it doesn't. I've got a new exponent. And I'm kind of embarrassed that I wasn't expecting this, because if I thought more carefully about it, I would have realized why it should have been there. So we found it numerical. So here's some measurements of it. If you put it back in and try to do your scaling class again, it works just fine. Okay, so there's clearly this new exponent to be calculated. So that was the good news of this. The bad news is I should have realized it was there. What is this exponent? Okay, basically you can just focus on what's going on right here. Right? We had to get the scaling to collapse here, and the rest was going to take care of itself. Right? This actually is related to a four-walker problem, at least for people's 1. So for the same argument as before, right, if I'm those two blue particles trying to survive in this C here, I only really need to know there's a left red neighbor that's diffusing and a right red neighbor that's diffusing. But I've got two particles there because this is what's going to contribute to that origin. This is what's going to contribute to my correlation function at the origin. I need both of them to survive. So you can have variations on four-walker problems because you can have different rules. But this is one where the two middle walkers can cross at will. I've got two lambs in the middle and two lions on the end. Okay? And so when we do the RG and get this exponent, we will have at least a perturbative calculation for a four-walker problem. So you go to do it, and let's see, what am I going to do? We'll talk a little bit about it. This is going way back to calculating that theta. Okay, this is actually not a simple RG analysis. It's fraught with peril. And let me illustrate some of the peril. Okay, this was the thing that was non-universal when those were rate constants, and it goes to something universal as the companies flow to their fixed point. I've developed a loop expansion. I've got everything in terms of, I really have two reaction rates, right? I've got the trapping reaction rate, and I've got the A plus A to whatever reaction rate. So that's what GR and GR prime are. But when I get my expansion in terms of renormalized couplings, I'm not supposed to have any singularities left. I'm supposed to have nice, well-reduced coefficients, and here this thing pops in. That's a problem. It's a sign that you haven't fully renormalized the theory. You either need to find some way to remove it or give up and realize that your theory's not renormalized. So this was encountered, like I said, by different people and dealt with different ways. First encountered by Martin Howard, and while I don't want to go too much into technical details, I'm going to just say a little bit about it from this point of view. What you basically have to do is renormalize your initial density. So all those diagrams that contribute to the B density have a B line, no pun intended, that looks like this. Okay. You can't do anything more complicated with that B line because it exactly comes in out and out of each vertex once. And basically what that is contributing to is that the initial density needs a renormalization factor, just like the coupling constant. It's not obvious, but if you put that in, you can actually show that it cures the divergence problems. And, so
that gives you the anomalous dimension?
No, well, it gives you a type of anomalous dimension. That was all back into that theta calculation that I didn't show you how to do. But, there. This calculation required that one way or another. And that's why it's a fairly technical calculation. And that's also why the crossover to B equals 2 is not so simple. So we need to do something like that again for our phi calculation. And I'm going to not say too much, but the main point is we're going to need to go to the BB correlation function. The easiest way to get it is if we can find the k equals 0 part of the BB correlation function, it'll have that exponent in there. And so you go to tree level and calculate that thing, and you get 0, and that's really fun. So you've got to go to first order. And I'm not going to say too much except that we counted the diagrams to first order, and that's the number of diagrams you have. So at that point, you either give up or you find undergraduates. I actually had 2 undergraduates over, not this summer, but previous summer, calculate all 59 of those diagrams. So we actually have a preliminary result for that exponent. I'm not confident, I'm not going to give the result, and we haven't published the result because I don't really think it's quite right yet. The problem is there's so much cancellation between those diagrams, you have to get every single symmetry factor right. I've got this beautiful mathematical notebook, it's conceivable I might be able to sort it out, but at any rate. Maybe. Okay, so what did we learn from this? First of all, RG methods and exact solutions are complementary. Sometimes we get exact numbers from these, and then we get statements about universality from the RG, and that RG justifies application for reaction diffusion equations for 2 dimensions. When you want to do some quick and dirty back-of-the-envelope solutions to problems, you can often get away with this technique. The critical dimension for the A plus B goes to 0 really is 2. It's just that at 4 dimensions, the reaction diffusion behavior changes. And basically, I hope I'm conveying that there's still lots and lots of things to calculate. We're not running out of problems anytime soon. After my 4th lecture, I'm going to sort of give a little summary of the outstanding, the major outstanding problems. But there's lots of variations, lots of calculations left to do. Relations between models. We may be trying to get a 4-Walker exponent here, and so forth. So I highly encourage people to be getting involved in the field. Thank you for your time.
Thank you very much. So the anomalous dimension is brought in the BB correlation for the correlation on anomalous. So that you're saying is because multiple particles can be between K particles. That's the reason, sort of. And
yeah.
That's the reason you need to be scaling.
Right. So basically, what I'm going to get out of this, I need to introduce a V0 renormalized. And that ends up influencing the B density. It ends up influencing the AB correlation function. But it influences them identically, right? So when I calculate my AB correlation function, divide by A and divide by B, right, that goes like the renormalized initial density over the renormalized initial density. That's why I didn't see anything there. But when I do the BB correlation, okay, as is often the case with these things, D0 squared has to be normalized distinctly. From B0. That's the nature of the pathologies of continuum limits is that the square of an operator is often very different. And you know this from delta functions, right? The square of a delta function is not a delta function squared. I don't even know what it is. But so we have to actually introduce new renormalization constants. There's new diagrams contributing to this that don't contribute to that. That's the origin of phi.
Yeah, but then it's very confusing because you have a very sensitive dependence on the initial condition, right? If you have lots of B's, say just by fluctuation in a section and have A.
It actually isn't, kind of paradoxically, it's not dependent on the initial density. It's dependent on the renormalization of the initial density. Yes, you do have an overall factor of the initial density that carries through. If I put in quite as many B particles, I will have quite the density later. But if you put in short-range correlations into B particles, irrelevant.
You think if I just start my initial condition where I just put lots of d particles together, that doesn't
Well,
change the result?
if you put in long range correlations, that changes things.
Okay, got it.
Other questions? Okay. There is none. We can close here, have lunch, and then we will see 1:30.